So far we have talked about binary search trees, BSTs. We talked about red-black trees, RBTs. And one important thing about both of them is that they are both binary. And as a reminder, for binary search trees, we have no guarantee on the height, in the sense that the height of the tree can be very, very big, because we can have a tree that's the form of a chain. And if we have n nodes in the tree, the height can be on the order of n. Red-black trees were provided as an option or as a structure that forces that height to be on the order of log of the number of nodes. Now I will talk about a new data structure that we call B trees, and these are not necessarily binary. Okay, not necessarily binary. When I say not necessarily, it means that they could be binary, they don't have to be binary. Okay, and that means a node can have more than 2 children in it. Okay, now the main motivation, the original motivation for B trees was storage on an external memory or on disk. Okay, so storage on a disk. So imagine that you have the data stored on the hard drive, not in the main memory. When you write a computer program and you declare an array and you do all sorts of operations on the array, sorting and comparison and addition and so on, it's usually the array is in the main memory of the computer, and operations and access operations in the main memory are fast. However, access operations to the disk are I/O operations, right? So when you have data on the disk, you are doing input-output operations, where every time you want to read something from the disk, that's an input operation. Every time you want to write something to the disk, that's an output operation. And these are much more expensive than the reading and writing in the main memory of the computer. So this structure, B-tree structure, was designed many decades ago for a case where you have the data is very large, that it resides on a disk. For example, B trees are very common, or B trees or variants thereof are very common in implementing databases. Okay, so when you talk about databases, you're talking about very large amount of data usually, and the data is all residing on the disk. Now, when we have the data, so imagine, for example, now I have million records. Okay, so let's actually try to think about why we need such a structure. So imagine that I have million records. Okay, so I have a database that has million records in it, and I want to search for a certain record. So imagine a company has million employees, and I want to search the record of a specific employee. And let's think about them that they are sorted according to some key. Okay, they could be sorted according to the employee ID, it could be sorted alphabetically by name, and so on. So we know something about how to find the record we are interested in a list that is sorted. Okay, and for that we can do, for example, binary search. Okay, binary search, or we can have a red-black tree that stores these records. Okay, so it can be actually an RBT, and we can do the search on this. Now, searching for a key, in this case, searching for a key takes us on the order, of course, of log n, where n is the number of records. So here in this case, it's going to take us on the order of log of million, which is about 20 operations, right? So if I am searching in a list of million records for a specific record, it's going to take me on the order of 20 operations. However, I go back to the point that now the data is on the disk. So now we are talking about 20 operations, 20 disk I/O operations. Okay? And this is a lot. I mean, for these applications, usually again we talk about applications in practice. We're talking about much larger data sets. So now we are talking about 20 disk input-output operations. Question is that can we reduce this number? Now, if you think about where did that 20 come from, of course the number of records is 1 million. Now when we did log of 10 to the 6, if I'm doing it in a binary search manner, I'm using read-black tree, the base of the log is 2. But now imagine that I can, for example, now have, log base 4 of 10 to the 6. If I do this, now this number now drops to about 10 operations. Okay? What does it mean to have log to the base 4? Now you are not looking at a binary search. You are now thinking about the tree structure. The node doesn't have 2 children. If it has 4, and every node now has 4, and so on. Now the height of the tree, if it is balanced, the height would be log n to the base 4. Okay? At a very high level, this is really the main motivation of B trees, that we want to go from binary trees to trees whose branching factor, or the number of children that a node can have, is more than 2, can possibly be more than 2. This way we can reduce the height. And now look what happened here. Just by going from a tree where the degree of a node is 2 to a tree where the degree of a node is 4, I reduced the number of I/O operations from 20 to 10. So I cut it in half. And this is significant. This is significant in practice because it helped me actually achieve or do the calculations we want in many fewer operations here. This is at a very high level, the rationale, and it sounds very simple, and it is really very simple rationale, is that let's not have just these sparse trees that are very, very long because they are binary and we cannot have more than 2 children. Let's reduce them by shorter trees. These trees are going to be shorter and fatter, wider, right? Because now at every level, we can have more nodes. And this allows us to, again, reduce the number of operations. But there are more, when we talk about the actual definition of B trees, you will see that they are designed in such a way that will give us also flexibility when we are inserting or removing nodes from the tree. So for example, when we are talking about 10 to the 6th records, and they are in the memory and they are sorted, and if we want to add one more element to it, then since we want to maintain the sorted list, then we have to push everything, for example. So we have to find the right place to put that element there. And then we have to move everything away. And if we have the structure that's capturing the data as a binary search tree, again, insertion and deletion are also going to be on the order of log and log to the base 2. And this is going to be also more expensive than when we are doing log to the base 4 or 8 or 10,000. Okay. Now, one other word I want to say before I go to the formal definition of B trees is that when we are talking in the language, for example, of databases, when we are talking about these records, okay, so this is record 1, record 2, and so on, let's say all the way to record million, we have this tree structure, something like this. Okay, this tree structure here that we impose on the records, this is what is referred to usually as index. Okay, so an index is a tree structure or a data structure. It doesn't have to be a tree structure, but in our case, the index is this tree structure that allows us to get to the record of interest that we are looking for here by traversing a path in this tree. Okay, now, for large amounts of data, the index is very large. This tree is very large to fit in the main memory. And now imagine that the tree itself, this data structure, is on the disk as well. And when the tree is on the disk as well, it's very important to think about how we access that tree. So Suppose that I'm going back to this example here and I want to look for this record here that I actually put as a solid circle at the leaf. If I want to look for this one, well, the first thing I need to do is get access to the root of the tree. To get access to the root of the tree, since it is not in the main memory, I have to do some sort of operation of reading from the disk, okay? So reading from the disk here, in this case, will be an operation that I can, for example, say disk read root, okay? So when I do this operation in my algorithm or in the pseudocode, it means that I went and fetched this node and all its information from the disk. So this is already one operation, one disk operation, one disk IO operation. Now, when I get this node, if the key I'm looking for is in that node, I'm done. But if the key I'm looking for is not there, I have now to find the child of that root where the key might be. So then I will look at this one here, but to get to this one as well, I needed to do disk read operation for this child. And the same thing here, I need to do this, and then all the way I need to do this one. So here, this is where we will see in the pseudocode of an algorithm for searching, for example, we are not gonna load the entire tree into the main memory and now do the search on it. Because again, the tree is too big to load in the main memory, and we are gonna actually load into the memory only the nodes we need. And this is, every time we need a node, we are gonna apply this disk read operation. It's going to go to the disk, fetch that node with its properties, get it to the main memory, then we are gonna do the comparison to see where the key is, and we proceed from there, okay? So again, this index structure, which is a tree structure that, imagine the case of a library. When you want to look for a book in a library, you have a catalog. You don't just go from one floor to the next, just scanning all the books. There's a catalog that you can actually say, where is the book that I'm looking for? It says the book is on the third floor, in aisle 5, on the whatever shelf, and so on. This tree structure is similar to a catalog that allows us, gives us the information, the directions of how to get to that record very quickly, okay? But this index structure, again, is on the disk, and accessing every node is an access operation that is costly, and we would like to minimize this number of access. And this is what the B tree is for. Again, it's a balanced tree, it's a rooted tree, it is for search, it is not necessarily binary, okay? So next I will define the notion of B tree formally.